Okay, folks, let's dive right into it. We're ready to get into Module 2, wave functions and the Schrödinger equation. And in our first learning goal in this module, I'm going to introduce the one-dimensional, time-independent, translational motion Schrödinger equation. And let's make that black. I don't know why that was. Okay, let's go for it. So the wave function psi, that gets a Greek letter psi, psi, is a function that describes all the dynamic information about a quantum mechanic object in a particular state. The Schrödinger equation is the equation that we use to find the wave function. And it's a rather simple equation at first, but as we're going to see, it will blow up into something complicated. So the way that this equation works out, this h hat, this is our operator. And the operator we're going to talk more about in detail, but that operator we can use to obtain information on a physical observable. Like if we use the energy operator, for example, that operates on the wave function. And after we carry out that operation, it returns the value in question. So in the case of using what we call the Hamiltonian operator, that is another way of saying the total energy operator or the Hamiltonian operator. So that will return to us the total energy of the system, and it gives back the original wave function. We're going to go into this in much more detail. So for now, I'm just going to supply for you the results of that when we plug in the total energy Hamiltonian operator. And we get the following for the one-dimensional translational motion, time-independent Schrödinger equation. We're going to see lots of these qualifiers. And it goes as the following: negative h bar squared over 2m times the second derivative with respect to psi of x. As it were, this chunk describes the kinetic energy. And now that's plus v of x times psi of x, where this v of x represents our potential energy. So we have the kinetic plus the potential. And then all of that equals the now total energy of the system times psi of x. So our goal in setting up the Schrödinger equation is to find a solution for psi, to find a solution for the wave function. So this is a second order differential equation, and there is a standard process to solve that. So I'm going to set that up for you now, and again, we'll go through this in much more detail in class. So the first thing that I want to do is collect like terms with like terms. And I'm going to do that by subtracting the potential energy over. And in this case right now, we're going to assume that v of x is a constant. And I'll use the letter v to describe that. So now doing that algebra, I've got negative h bar squared over 2m times the second derivative in psi. And now that equals E minus V all times psi x. So we'll often see, like instead of saying psi of x, you'll often see me just write psi x. So I subtracted that over and collected like terms. Now I want to eliminate the constants from this side so that I can just focus on the second derivative. So let's rewrite that again. I've got second derivative in psi. Let's see, that is a squared. Okay. And so now I'm going to push all those constants through to the other side, and I get negative 2m times the quantity E minus V, all divided by h bar squared times psi of x. Okay. And now at this point, I'm just going to leave this be. We are going to get into more detail on how we arrive at a solution for this, but there is a standard solution to describe this equation. So generally, that standard solution, we could think of in terms like this. So second derivative of some function f of x times some constant times the original function. So this is like our general standard form. This has the general solution, f of x equals cosine times, and actually, I'm going to just write kx, where k is a new constant that's collected all of the other constants. So that is our general solution for this equation. And if now I plug that in to be more specific for what we just did, we'll rewrite that as psi of x equals cosine times k of x, where my k is actually the collection of all of these constants. Let's see, oops, wrong button. And that equals, let me rewrite that. That constant k, it might not be obvious for us yet where this comes from, but we could write that as 2m times the quantity e minus v all over h bar squared and square root of all of that stuff. So this is the solution for our very simplified, one-dimensional, time-independent translational motion Schrödinger equation. So let's keep going down the rabbit hole a little bit more and play with this solution. Okay. And here I'm comparing our equations from quantum mechanics with our equations in classical mechanics, and again, specifically for translational motion, right? So we could describe the velocity of an object as the first derivative of its position with respect to time. We could describe the momentum of that object as the product of that velocity times mass. And notice the use of the vector quantities, right? It is important to specify that these are vector quantities. We could also write that the kinetic energy of this classical object is 1/2 mv squared. So this one we commonly know from physics. I want you to get used to seeing this formulation of kinetic energy as well. Momentum squared divided by 2 times m, which we could easily get to from this algebra right here, right? So, do the algebra, convince yourself that you can get to momentum squared divided by 2m. It's the same as 1/2 mv squared. And then now over here, I set up what we just discussed. And if you recall on the previous slide, we said that k was 2m e minus v. For now, if we call potential energy equal to 0, then my k solution just becomes 2m times the kinetic energy, in this case, divided by h bar squared and all square root. So I want to play with a result here in comparing these two. And I'm going to plug in our classical description of momentum and kinetic energy into this k solution and see what we come up with. So that's going to be 2 times m and times momentum squared all over 2 times m, all divided by h bar squared and all square root. So as you can see, the 2m and the 2m cancel. And I'm going to drop writing the vector quantity over momentum there to make this easier. So that becomes p squared over h bar squared, all square root, which we would recognize as just p divided by h bar. So this is pretty cool. If we were to compare that to an equation that we talked about in the previous module, which is the de Broglie wavelength equation, let's look at that again. So de Broglie wavelength equation goes as lambda equals h over p. So if we look at these two, we can see that they are inverse of each other and also different by a factor of 2 pi, right? If I consider that fact that h bar, let's write that over here, that h bar equals h over 2 pi. I could also rewrite this as 2 pi times momentum all divided by h. So why is this special? Well, if we think about this cosine function, so I'm going to go to the next slide and we'll rewrite all of these things that we just discussed here. So we've got, let's see, we wrote that k is 2 pi p over h, we note that the de Broglie wavelength can be written as h over momentum. And now if we look at our general property of this cosine function, so when we have this, regular old trig function, this k, it represents a wave number. And so specifically in, pure trigonometry, that k takes on the value of 2 pi over lambda. So if we compare this for just a moment and recognize there that I've got 2 pi and that quantity times p over h, well, p over h is the same as 1 over lambda. Thus, this k solution, let me rewrite that, is actually just 1 over the de Broglie wavelength. So 1 over lambda de Broglie, which means k truly is a wave number. So that's kind of cool. We just combined classical mechanics and quantum mechanics, and we came up with something that matches our basic trigonometry, that we get this value k, and it does take on the value of a wave number. It's 1 over the wavelength, in this case specifically the de Broglie wavelength. And as you can see right here next to me, I've got this Mathematica file so that we can play around with just this very general cosine function so we can see what the factors are. So we didn't have this a term in our previous solution, but I included it there because we're going to see it show up in other solutions. And recall what that a gives us is the amplitude. So a equals the amplitude. And you can see in my manipulate function right here, here it is, a times cosine kx. If I manipulate that amplitude, it just has the effect of decreasing the overall magnitude of the wave function, right? So the wavelength stays the same, just the amplitude changes when I change that a value. Well, k being a wave number will scale as 1 over the wave length, right? So if I increase k, as you can see, I'm making k bigger, I'm getting a smaller wavelength, which makes sense because they're 1 over each other. If I make k smaller, I'm getting a smaller wavelength, and that also makes good sense. And finally, I'll just remind you, if we go back to what our other solution for k was, that was 2m times the kinetic energy divided by h bar squared, all square root. So we can see there's also similar things going on there. When I increase the value of k, it decreases the wavelength. And as you can see, k and kinetic energy are directly proportional. So this all checks out. So we're really on to something here. We've got a good general solution from our Schrödinger equation that our wave function is in fact described by a cosine, by a wave. Awesome stuff.